Covalent bonding is a little more detailed than ionic bonding. So ionic bonding was pretty simple, as we just showed the transfer of electrons to get our charge equal to 0. Here for covalent, there's a lot more we have to remember. The first thing is that hydrogen and the halogens, which is, remember, your group 17, they can only bond with one atom. Okay, so they're never going to go in the middle. They're always going to be on the outside of your atom. Okay. In general, things to remember is when you're going to write out the order of your atoms, they definitely appear almost always in the same order as your chemical formula. Okay, now of course there's exceptions, but most of the time that's the rule you want to follow. So again, you're going to use your periodic table to decide how many electrons you have. So that's the same. That's not going to change. Basically, we're going to look at carbon here from this, and we know that we need 4 valence electrons. So if we want to, we can go ahead and put those 4 valence electrons in. And then we're going to look at our hydrogen, and each hydrogen has 1. So here in this case, carbon comes first. So what that tells us, carbon wants to make 4 bonds. If you see here, it's got 4 electrons that can pair up. So carbon typically goes in the middle. And then we put our hydrogens around the outside of that. Okay. Each hydrogen has 1 electron it can share, and then the carbon has 1 on each side. So what happens here is these just pair up. Every time 2 electrons pair up, we end up with a bond here. So sometimes these are represented with 2 dots. Sometimes you'll see them drawn with a line. What you want to do when you're done with that is you want to make sure your shell is full. So remember, hydrogen is full with those 2 electrons. So as we go around, we can see that each hydrogen has a full shell, and they're stable. And then we have to look here and remember that each one of these electrons is shared, so it counts both for the hydrogen and for the carbon. So carbon would have 1, 2, 3, 4, 5, 6, 7, 8 electrons, and then that makes it stable. So this would then be a completed covalent structure for methane. This shows you again that the electrons are being shared, the same one that I just drew here. They're being shared between both, so they're counted for both. The squares here are the same as the circles that I drew. Again, remember, hydrogen only wants 2, but everything else needs 8 valence electrons when you draw those circles. Okay, so bonding pairs, again, remember, I just showed you that 2 electrons here are going to be a bond. So again, sometimes they're drawn that way, and as you get more familiar with this, a lot of times we'll just draw a line here. It's quicker than trying to draw 2 dots. But those are still considered a bonding pair. Now sometimes we're going to have a situation where if we do those 3 steps, we're not going to have a full valence shell. So if we have our carbon here with our 4 valence electrons, we have our hydrogen, we have 2 of these. Okay, again, carbon wants to make those 4 bonds, so we're going to put carbon in the middle. So we would have 2 hydrogens, and then remember, oxygen is going to want 6 valence electrons. Okay, so we'll redraw this with our carbon in the center, our hydrogen here, 1 from hydrogen, 1 from carbon. Here, 1 from hydrogen, 1 from carbon. And then we're going to put our oxygen here. We've got our 1 from carbon. Okay, I'll draw these a little bit better here. And then we've got 6 with oxygen, so we'll draw our extra 5 around right here. So what we have to start with is 4, and then we have each hydrogen with 1, so 5, 6, and then 7, 8, 9, 10, 11, 12. So we have 12 valence electrons. So in this structure, we can only draw 12 valence electrons. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I only have 11 drawn. So carbon would have 1 more here, which is that 12th electron. What typically happens, though, is you do not have an electron, just 1 electron by itself. So this is our bond here, paired up. That's our bond there, paired up. Here's our bond here, paired up. We have a free pair of electrons here and a free pair here, which is perfectly fine. But then we have this one by itself. Usually that doesn't happen. So we would normally take that, we'll erase it here, and we would pair it up with this other electron. But if we go around, we don't have a full shell. If you look here with oxygen, there's 2 here, 2 here, and 2 here. So that only gives oxygen 6 electrons. So that's not a full shell. Carbon's okay with 8 here, and hydrogens are both okay. So what we have to do here is these 2 electrons have to actually make what we call a double bond. So they move over here between oxygen and carbon and make this second bond. So there's two bonds here. That's called a double bond. So right here, hydrogen has a full shell, hydrogen has a full shell. Now carbon has two there, and four here, so that makes 8. And now oxygen has 4 here, and then these two free pairs of electrons. 2 here and 2 here. So again, we can add a double bond. Now another way of looking at this is you can add up your valence electrons that are available, that they have. Then you can go back and say, okay, carbon needs to have 8 when it's done. Hydrogen needs to have 2 when it's full. This hydrogen needs to have 2, and this oxygen needs to have 8 to have a full shell. If we add these numbers up, we have 16 plus 4, which gives us 20. If we take the difference between the number of valence electrons that these atoms actually have, and then the number that they want to have a full shell, if we take the difference between that, we get 8. And if you divide that by 2, because every single bond needs 2 electrons, see, 2 here, 2 here, 2 here, 2 here, that tells us how many bonds we need in our structure. And if you look here, we've got 1, 2, 3, 4 bonds. So sometimes that makes it a little bit easier. So we'll go through that and practice that a little bit more too. Okay, so again here, a double bond is when 2 pairs of electrons are shared between the same 2 atoms. A lone pair of electrons are pairs that are not shared. Okay, so they're basically only going to count for 1 atom. So our oxygen there had a lone pair here and a lone pair there. Double bond here in the middle, you can see 2 pairs are shared between 2 atoms. Now you might note that when I drew my structure, my oxygen was down here. Technically it doesn't matter as long as the carbon and the oxygen are bonded together. Okay, so sometimes a double bond isn't going to be enough. So let's look at this example. This time we have 2 carbons, 4 electrons each, and we have 2 hydrogens that have 1 valence electron each. So if we add those up, 4 plus 4 is 8, plus 2 more gives us 10. Carbon wants 8 to be stable, and hydrogen wants 2 to be stable. So again, 16 plus 4 gives us 20. So now the difference this time is 10, and if we divide 10 by 2, that tells us we need 5 bonds in this structure. Well, if you put carbons here in the center, and then remember, hydrogens have to go on the outside because they can only form that 1 bond, we only have 3 bonds here. Hydrogen's full. It has a full shell, 2 electrons, 1 from carbon, 1 from hydrogen, so we can't add any more bonds with our hydrogen here at all. But here is telling us we need 5 bonds in our structure. So what we have to do is make what's called a triple bond. There would be 2 electrons here, 2 here, and 2 here. And now if you look, carbon would have a full shell on this side, and carbon would have a full shell on this side. So there may be times where you do have to have what's called a triple bond, where you have 3 pairs of electrons being shared between 2 atoms. You'll never have more than a triple. Okay? So here just kind of shows you the shorter the bond becomes, the more bonds are between. So a single bond is the longest, triple bond is the shortest. So the shorter they become, the stronger they become. So a triple bond is going to be the strongest bond, a single bond is going to be the weakest bond. And those are your covalent bonds and how we make structures with covalent bonding, sharing of electrons.